Good morning, everyone, and welcome to Physical Science 110. Today is September 27th. We are in week 7. We are continuing the concept of basically thermodynamics. We finished actually the part that has to do with the principles of thermodynamics and all, but we're going to be dealing with heat transfer, which is really a different topic altogether. I mean, it really stems from the heat and how we find heat and measure heat and all of that from the first part, except that it deals with really how heat transfers between media, okay, or lack thereof, because heat can transfer even in the vacuum. That's something that is unique. I mean, it's really something that we have to explore. Okay, so that's the topic for this week. There was a message I sent this morning around 7:30 in the morning for all of my classes, including your class, and also for the 4 sections of astronomy I'm teaching this semester. And that is, I will be on campus this Thursday in the morning, really. I mean, I'm available at least for the morning for you guys. If you want to meet, you really have to send the request as soon as possible. No later than noon on Wednesday, because I'm putting a cap on that so that I plan my day correctly for me to also probably meet with the faculty and all the things, business I have to take care in there. So I'm going to be on campus this Thursday morning, mainly really for you guys. So if you want to meet, I will be more than happy to meet in person. If you don't know where my office is, I can send you the information of where the office is. But I'm going to be in campus for you guys all morning. So if you want to meet, send me a request. Because of the fact that I have so many classes, the availability is going to be limited. So if you really want to meet, you really have to send it as soon as possible, so that it's going to be on a first come first base served. Basically, that's how it's going to be. Okay. Of course, you still have the option to meet online if you anytime. It doesn't have to be on Thursday. It can be anytime. But this Thursday, I'm on campus, and I'm going to be available for this meetings and all. Okay. Drive safely, okay? Okay, good. So the point is, if you want to meet, like I said, please do send a message as soon as possible. That's the message that I sent at 7:30 this morning for everybody. This week, as I was saying, it really has to do with heat transfer, how heat goes from one medium to a different medium, or from one place to another place, even in the absence of media. Heat reaches us from the sun to Earth, and there is vacuum. There is nothing between us and the sun. So it travels in vacuum too, okay? So there are 3 main processes that you need to remember. 3. 2 of them require medium, and 1 of them can travel in vacuum, okay? The two for medium are conduction. Basically, you have material. I'm going to take this example because this is a poor conductor, but it's still, you have 2 examples in here. I have a rod that is made out of basically a plastic material, basically. This is a poor conductor. It is a conductor nonetheless, but it conducts very, very poorly heat, okay? So if I'm interested not to conduct heat, if I'm interested in the insulation, then this is probably a better material for me. If I'm interested in transferring heat, this is a conductor. Iron is a conductor, okay? So if one part of the iron is hot, I put it next on a hot source. And if I put my hand on the other side and I wait a little bit, I will find that my hand is getting hotter. So I say in this case that heat was transferred from the hot source to the cold source. Here is question 1 of the day. If instead of putting this end on a hot source, I put it in contact with ice, for example, I will notice that my hand on the other end will get colder. Can I say that cold has been transferred from the cold source to my hand? What do you guys think? Okay, that's kind of tricky question. Let me answer it again. Let me ask the question again, okay? If I put a hot source in here, okay, it gets hotter and heat will propagate through the iron until it reaches my hand. My hand starts to get warmer, hotter and hotter, the longer I put it in contact with this iron. I say in this case that heat was transferred from the hot source to the cold source. That I understand. There's no question about it. Now here is a question for you guys. If instead of heat, I put ice in here, obviously, if I wait a little longer, this portion of the iron becomes colder and colder until it reaches my hand and it becomes colder and colder. Can I say that cold has traveled from the cold source to the hot source via this conductor? Let me put the question in the chat session in here. Can cold travel from a cold source to a hot source? This is the question of the day, one of the questions of the day anyway. You have two choices, either yes or no. Yes, no. Come on, guys. Somebody thinks it's a yes, and it's probably a weak yes from the expression of her face, but I need to have the other people tell me. What do you guys think? Okay, somebody changing her mind to no now. Okay. Okay, Sabine, you came in late. Let me ask the question again, okay? Since you came in late and you deserve, you're entitled to it too. Here is the scenario, Sabine. You put a hot source in here, furnace, okay? You put this end of the furnace, and going to get hotter. If I have my hand on the other end, the heat will travel from the hot source to the cold source, to my hand, and I will feel warm at the end of the day. It's going to get hotter and hotter if I keep on holding it this way, okay? No problem with that. This is daily experience. If instead, that's the question, if instead of putting ice, would cold travel from the cold source to the hot source? I know some of you are leaning to yes, and I'm trying to push you away from it because the answer is no. Okay, the why is even when you put ice in here, heat is traveling from your hand, which is warm, toward the ice. That's why you feel cold, because you're losing heat. Make sense now? Okay, very good, very good. So heat always travels from the hot source to the cold source, even if you put ice. So what you're doing in this case, you're melting the ice with your hand via the iron. So you have ice on this side, and you have a piece of iron connecting you. So the heat is basically being drained from your hand continuously toward the ice until it warms it enough to melt. So in that case, the answer is no. Cold never travels from a cold source to a hot source. It's always heat that travels from the hot source to the so-called cold source. Even in the first scenario, I mean, in the first case, it's obvious because you have a hot source and you have a cold source. Okay, so this is clear. Okay, so the answer is no. Heat always, so let me put the answer for you guys. So the question was, can cold travel from a cold source to a hot source? No. No. Heat always travels, let's put it travels in parentheses because the word travel in here, from a hot source to a cold source. Always. Okay. So that's the answer to the first question. So hopefully you guys have no question about it. So let me share with you the screen so that we're looking at the same stuff as normal. So let me get the objectives for this week. Again, the three main ways for heat to transfer are conduction. The one I was describing earlier is conduction, with a piece of metal, and materials fall into two groups: good conductors like iron, bad conductors like glass or wood or air. They're bad conductors. Air conducts conducts heat for another reason though, for convection. Convection involves the movement of a fluid of some sort. Air is a fluid. So the way air transfers heat is not via conduction. A stagnant air that is not moving at all is a poor conductor. But because of the difference in temperature, one portion of the air is hotter than the other portion, the density in one side is higher than the density of the other, and now the density wants to become uniform. So the mass of the air moves from the section that is more dense to fill the gaps in the less dense. In doing so, it drags with it the temperature and basically keeps this circulation. Usually it's a cyclic operation. It goes in circle. Okay. Radiation does not require a medium, conductor or no conductor, does not require air or fluid, water, for example. Radiation travels in vacuum or in media also. Radiation is electromagnetic radiation, the electric field and the magnetic field going from point to point to point, carrying with them the energy, which is the heat in this case. So those are the three means of conductions. Okay. Let me, the person who's in the car probably is having issues with connection as they move from point to point. That's why we're seeing this. Okay, let me stop sharing the screen because there is an important aspect that I want to explain in detail about this one. So let me first of all pull the one until I find the, and let me add another tab in here and let me call it week 7. And let me explain the difference between them. I know this is not a substitute for what you guys are going to be doing in lecture, in the book, but just to explain those points so that you guys see them. So let me go in here. Let me find the pen. And let me talk about the three of them. So the first one is conduction. So conductions, I have a point in here, I have another point in here, and I have an element between them. So this is your conductor. Okay, so this is the thing that connects the two media. You have a place that is hot and place that is cold. For example, the outside is a hot place. The inside is cold because probably you have the AC going. So in this case, those are the two regions. They are separated by a wall. So the wall in this case will be my medium between them. It could be a conductor, it could be an insulator. In the case of a wall, I really want an insulation. I don't want conduction. Yet heat still travels. Heat always goes from here to here. This is the direction of heat. Okay. So this is the first one. Obviously, how much heat will go depends on the size of this object. If it is narrow, like this one, there is little heat that can travel. It's throttled, if you wish. Not too much goes through it. But if it's open like this one, there is you can conduct more. Okay, think of it like a fluid, like water, for example. If you have a narrow tube, yes, you can have fluid go through it for the same rate. There will be more fluid going through this one than through this one. Okay, so that is one thing. So the cross section or this area matters. If you want insulation, you would want to make that section as small as possible. That's one problem. Okay, so that is one thing. The other thing also that it depends on is the length. The longer it is, the less basically heat will travel. I mean, will be because this one and this one, the two regions are very close from one another. There is more heat that is going to be drained than between these two regions that are far away from one another. So this is still hot, this is still cold. So the length matter. The last thing that matters is the different materials. I already mentioned the fact that they have conductors and insulators. So materials, they come in different fashions. They come in a conduction, good conductors, and good insulators. If you're building a house, for example, you would want insulation. You don't want conduction, okay? But if you're trying to build, for example, a stove, something to put on the stove to cook with, you don't want heat to be not conducted. You want heat to be conducted. So you would want the pot to be made of a material that conducts heat. You put the pot on top of the stove and you turn on the stove, you would want the heat to go from the stove toward what is inside the what you're cooking. So you would want that material to be actually a good conductor. So depending on the application, you would want to get the materials where you want them. So if you go to Home Depot, for example, and you have probably a leak somewhere in the house where heat is still getting in from inside, or heat is escaping in the winter. The outside is very cold and you would want the house to be warm. So in this case, you heat the house. So what happened in this situation, you don't want that. So you go to a place where to get the insulation and you put it in the place where there is a leak, and you would want to have that material in there. So that is basically what this thing is. There is actually a formula. I'm going to write it symbolically in here, okay? The heat rate flow is usually, I'm going to put a number in here, but I'm going to write that one in there later on. So the longer the object is, the less heat flow. So the length needs to be down, the area needs to be up, and the conductivity of the material is here. So this is basically how you write it. How much heat flow, how much I'm losing heat, this is the expression for it, okay? So this is the first type of heat transfer via conduction. The second type of heat flow is convection. Convection, you have a fluid. So you require a medium, which is a fluid. So you have a fluid, and that fluid is sitting at different temperatures. So one side in here, it has a cold, and this side in here, it's hot. I try to draw it as a pot, but doesn't mean necessarily a pot. It could be, for example, like this. This is fluid, water, for example. Ocean, and this is land. This one is a different temperature. Let's say, for example, daytime. Daytime in here, it's hot. And in here, it's cold. Here is the thing with this one. It's not heat via contact as much as heat via matter transfer. The air in here, the mass of the air in here is dense, sir. This mass in here is loose, okay? Less dense. Less dense. So in this case, the material flows in here. So the air mass moves. Okay? The air mass moves. When it moves in here, it expands because it was at some point too dense. Then it's going to expand because in here it's hot. And in doing so, it's going to rise. And then because the upper atmosphere is lower temperature, so it condenses again in drops. And that is how the cycle in the front of the ocean is. So for example, if you light the fire during daytime, it's going, the fire, the smoke is going to go this way toward the land. During nighttime, because of the high specific heat of the water, in this case the ocean, its temperature rarely changes with the day and night. However, the land changes drastically. This is in the presence of the sun in here. So the sun is somewhere in here, okay? And the lack of the sun, when there is no sun, this is still the same area that I was talking about. So this is still ocean. And this is land. Now I don't have no sun. So this temperature drops and becomes cold. And this temperature hardly changes, so it becomes hot. It does not change between day and night as much as this one does, the land. So in this case, the air in here becomes more dense and the air in here becomes loose. So the mass of the air now moves in this direction. And in doing so, it's going to expand above the ocean, rises, and then condenses again and drops on the other side, and you have this monster. So if you do a fire in the evening, for example, on the beach, the fire, the smoke in this case will travel, will be carried with the air as it's moving toward the ocean. Again, this is how weather in general is happening. So weather in general is really related to convection. I mean, if you look at your pot in here, the one I was drawing in the beginning, this place is hot and this place is cold. So the air in here is denser, so it's going to drop. And then as it drops, it expands. And then as it expands, it becomes less dense. So it's going to rise. And as it rises, it's going to be denser, and so on and so forth. And you have this rotation. So this phenomenon, convection, is a very critical aspect of the heat transfer. And it plays a major role, for example, in the lower layers of the earth, in the mantle, for example, to understand geology. And it plays a major role on the surface of the earth, because that's how weather is happening. And it plays a major role on different planets, for example, on Jupiter, all of the other planets that have atmosphere of some sort. So it plays a lot of in the dynamics of the atmospheres in general. As a matter of fact, it plays a major role for the heat that is transferred to the earth, because the heat in the core of the sun is super hot, because it's a millions of degrees, and whereas on the surface, it's only a few thousand degrees Kelvin. So if you count 1,000 Kelvin, 6,000 Kelvin versus in the core, which is in the millions of degrees. So again, at some point, there is a convection layer, and that convection layer takes the layers that are cold in the top and drops them in, and the layers that are lower, that are hot, takes them outside to basically relieve the heat. So that's how the sun loses its heat. So convection is a critical aspect of the process. The formulas in here are a little bit more complicated, but this is basically the principle behind it. The last process, the third process we'll talk about, is radiation. So radiation happens with electric field and magnetic field. Part of it is what we see, the visible region. So for the radiation, basically, if you take a piece of iron, this one, for example, or any material for that matter, and you heat it up, as long as it doesn't really first of all, go through phase transformation. And phase transformation is a critical aspect, meaning it liquefies before it becomes liquid. Its temperature starts to rise, okay? Before it changes phase, it goes to another form. its temperature starts to rise, and you will see it actually changing color. From a dark color like this one, it starts to change to a dark red, then a red, then it's going to go through even more temperatures. If you keep on heating it before it melts, it's going to change to white color. And if it doesn't melt, it's going to change to all of the spectrum lights, basically. But for iron, it's not possible because we know it's going to transfer. And for other materials like lead, for example, it melts very, very low, around 500 Kelvin, 500 degrees Celsius. So it's really not a good thing to work with. So it depends on the material. If it does not go through a phase transformation, it's going to heat up. So what's going on in here? There is a law that connects the frequency with the basically the heat that is emitted in this case. Okay, so there is a dispersion law for low frequencies. Low frequency, the curve looks like this. For a high frequency, the curve would look like this. It peaks around that frequency. That is where the peak is. This is called the dispersion law. I'm sorry, the displacement law. Okay. So this is basically, this law was well known. For even higher frequencies, there is less peaks in here. Of course, less heat in here. Obviously, less energy in there. Obviously, if the frequency increases higher and higher, the temperature. So this is the temperature. I'm sorry. This is the temperature. So this temperature is less than this one. So this is a low temperature. This is a high temperature. So the temperature and the frequency, they seem to be connected to one another. Usually this one is not written in terms of the frequency, but written in terms of the wavelength. It's still the same thing because the wavelength and the frequency are related to the speed of light. Because again, this is light. Electromagnetic radiation is light. So it's usually the wavelength times the frequency. So if this temperature is proportional to the frequency, it's inversely proportional to the temperature, that's all. This is C. This is 300,000 or 300 million meters per second or 300,000 kilometers per second, doesn't matter. So this is the fixed number for most part. So this is a law that explains this radiation. People try to understand this one. In doing so, they ended up with something called the black body radiation as a model for this one. And the black body radiation, the black body is a body that is a good emitter of radiation, which means it's a good absorber also of radiation, absorbs well radiation. Hence, it appears black because every radiation that it hits it is absorbed. So there is nothing coming back versus a white body that is actually perfect reflector. Perfect reflector in this case will, if it's hit with the radiation, it emits it all back, so it appears white. The combination of all the different spectra looks white. Just like when we see outside the white objects that are white because of the fact they reflect all of the radiation. So a good reflector, it's also a good emitter because in the same time, if you heat it up, it's going to emit all the spectrum. Good absorber is also a good emitter, which is the second point of discussion in here that I really want you to make a distinction about it. Okay, there is a second point in here. I'm going to write it in here on the screen. Good emitter is a good absorber. Okay, this is a black body. So this is what we study as a black body. By the way, it's only one word in here, okay? We call it the black body radiation. So the model we try to study is this one. This is an ideal system, of course. Black body radiation, 100% reflector, emitter, or 100% absorber. Of course, when you say 100%, it's really an ideal thing. There is no such a thing, 100%. It always is going to reflect some when it's absorbing. It's always going to absorb some when it's emitting, okay? Same thing, a good reflector is a good so a good reflector is actually an example of that is a wide body. So let me just stretch. This is usually not of interest to scientists, okay? In other words, a good reflector has an emission rate of 0% in a year. It emits nothing, okay? So this is the second point in here. I really want you guys to make that distinction between these two bodies. Again, these are ideal situations, just as I was making the distinction between a conductor and an insulator. A conductor, when we talk about an ideal conductor, that is an ideal one when we say it's 100% conductor. There is no such a thing. All metals, by the way, are good conductors of electricity and good conductors of heat. All non-metals basically are also insulators of electricity and also insulators of heat, but you have an exception in this case for heat because you have to take into account the convection. A good insulator of electricity is air, for example. Otherwise, we will have electricity flying from the plug. Okay, and good thing that it's an insulator so that we don't get electricity just because of sitting in the air. Okay, that is thing, but it's a good conductor or an insulator also of heat if the air is stagnant, is not moving. But the air moves, so we have a different process involved in this case, and namely the convection. So this is in a nutshell, basically the ideas from this chapter. Let me go back into my the notes from this week, so that we're on the same page. So let me stop sharing that screen and share with you guys the notes from this week. So again, we talked extensively about conduction. As a matter of fact, we talked a little bit more than what the book has said in here, and also convection, radiation. I mentioned the displacement law, okay? Newton's law of cooling. Okay, here is the idea behind it. If the gradient in temperature, if the difference in temperature is small, in this case, the rate at which the flow is little, it slows down a lot. In other words, if I have a cup of coffee, for example, that is barely warm, it's going to cool down and take a long time for it to cool down. Whereas if I have a cup of coffee that's extremely hot compared to the environment, it's going to cool rapidly in the beginning. And as its temperature drops, it's going to slow down, okay? So this is called the Newton's law of cooling. So this is a phenomenon that we take advantage of, okay? If the gradient in temperature is not, let me explain why this is critical in here. And I know you guys are receiving a lot of messages basically from either TV, from the news media, from everywhere, including from the power company, basically about the temperature. You know, the setting on your temperature, the thermostat. If it is too hot outside, let's say, for example, it's 110 degrees, which is extremely hot, okay? You don't want your thermostat to be extremely low because that puts tremendous gradient in temperature and puts your compressor work extremely hard to maintain that gradient, okay? If for some reason your compressor or your AC unit fails, there is tremendous loss of heat in this case to the outside because of that tremendous gradient between inside and outside. If you set your thermostat higher, in this case, the compressor does not work as hard. Your AC unit does not work as hard. If outside is 110, and for example, you want your inside to be 60 degrees, then in this case, you are looking at 50-degree gradient, and that is where you have a lot of work. And that is actually what causes actually the AC unit to work extremely hard. Sometimes it breaks. But if you set your temperature, let's say, for example, 80 degrees, I'm not saying you do that, but let's say, for example, you put it at 80 degrees. The gradient in this case is only 30 degree between the outside and the inside. So in this case, it's still high, but in this case, it's not as bad as between 110 and 60 degrees. So this is really the point of it. It is coming from this analysis in here. So that's how you understand that, okay? So the moral of the story is, if you would want really a lower bill, if you would want to maintain your AC unit for a longer time, And if you don't want to stress it further, and if you don't want to cause your heat to be tremendous outside, if there is a leak in there, set the temperature higher. Don't set it at, I know it doesn't feel as comfortable as 60 probably. 60 is too cold for me, honestly. But if you set it, it's not probably what you want, but it's a lot comfortable, much better than 110. So that's the point of it, okay? So this is one thing. And then the greenhouse effect. The greenhouse effect has to do with the atmosphere, which when it has more of the two culprits, namely water and also carbon dioxide. What happened in this case is that the sun's radiation, which is this process that I was talking about, and how heat is actually coming from the sun to begin with, comes in different frequencies, different wavelength, and goes through the surface and is absorbed by the earth. Because the earth absorbs that radiation, it must get rid of it, and the only way to get rid of it is by radiation. By the way, we also are sitting at room temperature, and we also emit radiation. So if somebody tells you glow, they are not wrong. They are exactly right, okay? Because of the fact that we emit radiation on our own. And that's the principle behind the goggles, by the way, used to look at people, for example, at night, or look at animals at night, because of the fact they have a given temperature inside their bodies. And there, in this case, the outside is cooler versus their own bodies. So in this case, they result in a net emitter. Hence, you can detect them. Okay. Whereas if the environment outside is hotter than the body, in this case, they will be a net absorber. So in this case, it's very hard to detect them because you don't get the radiation back to your goggles to see them. Okay. So if you would want to not to be detected by those goggles, probably wear something that absorbs all the radiation and insulate you, and maybe you can also be not seen. Okay. So that is actually the idea behind it. So in this case, when the radiation comes in, it's absorbed by the earth, and then it's going to be emitted back. And usually when it's emitted back, because of the heat actually sits in the infrared has a specific wavelength. Now the infrared, when it tries to go back to escape to the atmosphere and basically leave the planet, does not really do so, because it falls in the infrared. It's actually absorbed by the water and the carbon dioxide in the atmosphere, and those, they absorb it and then re-emit back. So in this case, that form of heat is trapped in the earth, and this will go on and on. So greenhouses that you see them outside in the farms, they use this principle to take advantage of the fact that you would want to trap the heat for the green stuff to grow. And hence the name greenhouse effect. Okay. This has initially a desirable effect because it warmed the earth good enough so that it had the life evolve on it. But now it actually has this undesirable effects, that in that it's really going to cause the earth to even warm further and cause basically life to suffer from its consequences. So this is basically some of the topics covered in here. Then we have the phase transformation. I mentioned this briefly. When the temperature is changing, at some point, when the temperature is increasing, at some point, that energy, instead of raising the temperature of the object, it's going to go toward the object to change its phase, to change its form. For example, liquid water sitting at room temperature 20 degrees Celsius, if you put it on a furnace, it's going to go and rise in temperature. It reaches 21, 22, until it reaches 80 degrees, becomes so hot. In this case, around 70 degrees, eggs start to boil. Start to cook, basically. That's what boiling of the eggs is. Boiled eggs are. And then at 80 degrees, 90 degrees, 99 degrees, it's still water. At 100 degrees Celsius, that water, if you add more heat, it does not raise its temperature. It's going to go from liquid water to gas water, which is in this case vapor. So it's going to evaporate. So any more additional heat will evaporate that water until all of it is gone. So we call that one the latent heat of boiling, whereas the fusion goes from the solid to liquid. Okay, each material has its own characteristic. In other words, how much energy is really required to break the bonding, the chemical bonding for it? That is what is happening in this case. Okay, so that is what's happening in the material. So the melting and the freezing, that's That's the other operation opposite to the boiling, the one I was describing. So we go again from liquid, then we drain energy from it. We take heat from it. Like, for example, the AC unit, that's all it does. It takes heat from it and then dumps heat outside until its temperature cools down to a certain point. Then it goes through a different phase transformation where now the atoms or the molecules start to get closer and closer and they form new bonds and the material changes form. Instead of being liquid, it becomes solid. Okay. So this is basically the energy is the latent heat I was talking about, how much heat is needed to change from liquid to solid, or from liquid to gas, or from solid to liquid, or the opposite in this case, from gas to liquid, from liquid to gas. Okay, those are the three main phases that we know on Earth. Okay, this is in a nutshell the content for this week. Let me go back into other stuff happening in this week. So the discussion are the couple of items I mentioned so far. Okay, the first one has to do with, can cold travel from cold source to hot source? And the answer is no. The second one has to do with the good emitters and good absorbers. Okay, and then we have a quiz this week. Okay, it's open actually. It has only 46 questions. It's the topics from last week. And last week's topics has to do with thermodynamics. Okay, this is a summary for them. So if you click in here, these are the concepts that we covered last week. So you need to go back on them and understand them and so on and so forth. And then take and do the reading, read the materials on the book, read the chapter. I know I posted the PowerPoints from last week, but those PowerPoints are just a summary, just as much as the discussion I have with you guys today and last week and so on and so forth. They're just the summary of those. So you still have to go through the book and make sure you're ready for them. You have 3 attempts for this quiz. It's due October 9th. October 9th is not this Saturday, but next Saturday. Okay, please do not leave it until Saturday and start working on it and then ask for extensions, because I will not give extensions. So start working on it soon, this week, before anything else. Okay, because this is stuff from last week. This is not this week's materials. Okay, and then take care of it. So you have 3 chances, takes only the highest score. Each time you try it again, the questions change on you. So make sure you understand the materials before you actually go through all of your attempts. Okay. So this is what's happening this week. Okay. Do you have any questions for me? Yes, Sabine. Froze. I don't know. Okay, very good. Very good. Okay. So I'm gonna stop the recording. And if you guys choose to meet on Thursday, I will be more than happy to arrange for that. Thank you.